So please rate this session. That was a very good talk, by the way. I like that he actually kind of trolled me. I enjoyed that. Achievement. So yeah, please rate the session and also use the app to ask any questions. At the end, we will have some time to answer those. So, how many of you have ever read this phrase? Okay, basically, mostly everybody knows the famous software is in the world. And the thing is that I've read this before, and I believe it, right? But it is sometimes hard to understand up to what point. And not only more and more companies keep on writing more and more software, but also those pieces of software keep on getting more and more complex. And there's many ways of measuring complexity. One of them, which is not necessarily a proxy for complexity, is the number of lines of code. And so what I decided to do was to go a little bit over the history of the software that I do remember, and trying to figure out how many lines of code it had, and trying to figure out whether it's growing, or it's accelerating exponentially or not, or maybe it's staying the same. So, Adobe Photoshop, pre-color thing. This pre-old style, this from 1989, and it had 128,000 lines of code. 128,000 lines of code, for me, actually feels very small nowadays. If you do npm install of anything, you already passed that, for sure. Right? So this is actually pretty small, and this is a very, very useful piece of software that everybody was using. So, maybe 128,000 is enough. Then we go to 1993 with Windows 3.1. And this one was a serious piece of engineering, because I was able to play games on it, including Prince of Persia, the old one. And it was great. And it was already 4 to 5 million lines of code. And this is an OS, right? So no OS, 4 or 5 million of code. Cool, we're there. We don't go farther than that. Well, OpenOffice is not an OS. It's just a piece of software that we run to write documents. 9 million lines of code. Chrome, 18 million lines of code. Who remembers this? Windows Vista, I keep on saying Windows Vista. Windows XP. Windows XP had 45 million lines of code. And that's a lot of code, right? This is a car, yes. And it's a Ford pickup, and it runs 150 million lines of code on the car. So if you think about being in this car we are all engineers, we know that, per million lines of code, there's at least a bug, let's be honest. That means you have 150 bugs running your car, which scares me a lot. And the worst part is that we all know that code is, the way we write code is actually not evolving that much, right? So since the beginning, since we were writing, since someone wrote Photoshop, until that car that is running 150 million lines of code, yes, there's been a lot of changes on the way we run the code, on the way we compile it, even the programming languages. There's been changes on continuous integration, continuous deployment. All of those things were great. There's been some changes in the way we write the code, right? We have better editors. But I'd say that is pretty incremental change. Editors are getting better, but it's not 150 million times better than Photoshop, right? It's increasing a little bit, but it's still not getting there. Google, 1 billion lines of code. And Google is interesting because the way Google writes code is actually quite different. The amount of tooling that a Google engineer has when they're writing code, which is similar to the one that a Facebook engineer might have, it's huge. To the point that if you've ever worked at Google, I did. I used to be a senior software engineer at Google. When you leave, you're like, oh, what? I don't have Blaze, I don't have Grok, I don't have, there's so many different tools that internally at Google are great and make you a better programmer that when you leave, you miss them. So tooling is the most important thing, I think, for engineers, right? We are writing code, we use tools, we need to be masters of those tools. And the problem is that those tools have not really evolved. So while creating something is still possible and definitely doable, it takes a lot of effort, right? If you want to build something like this, absolutely, you're going to be able to use the hammer and things like that. Well, I will not personally be able to do it because I'm not good at building houses. But if you want to build this, with some skill, you'll be able to do it. But using those same tools, if you want to build something like this, now that's different, right? Even planning for this is a huge piece of engineering. And if we gave the architect, Calatrava, we gave him just the hammer that we had before and no computers or anything like that, it would be a very interesting thing to see. So that is why I'm going to be talking today about machine learning on source code. What we're trying to do is use machine learning to improve the toolings that developers already use. So I am Francesc Campoy, and if you were here before, I was here before too. This is my second talk of the day, and I'm very jet-lagged. I am VP of Product and Developer Relations at Sourced, and what we do is machine learning for large-scale code analysis. And I'm on Twitter if you want to find me and ask questions. So we're going to be talking about machine learning on source code. So first I will define what is machine learning on source code in one. What is the field? What is the difference between machine learning and source code and all the fields of machine learning? What is the research? Who is doing research on this, and what are the things that we can apply today and that work? And then we're going to see how we can actually use that research to improve our tooling. And there's going to be a bunch of different live demos on the way. And I'm not able to open the bottle. So, machine learning on source code, what is it? It's actually simply machine learning for which the input is source code. That's it. So if you think about machine learning that it's learning from videos or images or natural text, all of those things are different, slightly different fields of machine learning. You can call it computer vision, NLP, all of these things. Machine learning on source code is simply the one where the input is source code. And it is related to many different fields. One of them is data mining, because as any kind of machine learning problem, we need a lot of data. We need a huge amount of data. And luckily, we have them, right? Like that car is running 150 million lines of code. How much code is there on GitHub? I asked this question, and they don't really know. But we assume that it's somewhere around 3 billion lines of code on GitHub. But that is our assumption, not GitHub's. So we'll figure out eventually. Also, natural language processing. When you're doing natural language processing, you're working with very similar things as programming languages. You do have syntax. You have syntax trees, except that they're abstract syntax trees. You have tokens, but those are words. So there's a lot of the same techniques that we're using for NLP that you can actually apply them and translate them quite easily to working with source code. There's limitations and differences. The main one is not totally correct natural language is understandable. Not totally correct programs do not compile, right? So when we're generating things, it's actually way harder to do, but still should be doable. And then there's a lot of graph-based machine learning. And I put this because this is the hardest part of machine learning that I've done so far. Learning from sequences, it's kind of doable, it's pretty easy. Learning from graphs actually requires understanding how to slice a graph into meaningful pieces. And we'll see a little bit how different people do it. So what do you need to do this? Well, lots of data, like lots of data. And then the fancy ML algorithms that we're going to discuss, I'll show you a little bit the kind of different models that we can use, neural networks, and the different kinds of neural networks that we're going to use. And also a little bit of luck. When you are training an algorithm, there's a lot of different factors that might bring you success or failure. So very often when you're doing research, you're going to see people running the same models with many different meta parameters and trying to figure out which one works better. It is not only logic. You cannot predict which is going to work better. You need to train it many, many times until you find something that actually works for your problem. So let's talk about the first challenge, which is, as I was saying, data retrieval. There's a lot of data in the world. So when we think about ML on code and we talk about data, normally everybody thinks about GH archive, which is a GitHub archive, and basically it contains the metadata of GitHub, right? So the list of repositories, their names, their URLs, and also a number of stars. But it does not contain the code, right? So it is not a huge thing, because finally it's only metadata. But what we need is actually source code. So we created this data set. It's called public Git archive. And what we did is we downloaded all of the source code for all of the revisions, for all of the repositories that had 50 stars or more on GitHub. And that is around 3 terabytes of source code. We did that this year. Our OKR for next year is actually do it for all repositories. And if we're done with that, then we're going to start adding other things. GitLab, Bitbucket, but also the Eclipse Foundation, Linux Foundation, all of these different Git servers around the world. We want to download all of that thing to have that data available for researchers. It is much larger than any data set of the same style that has been created before. So we have 182,000 projects compared to around 1/10. And the size is 3 terabytes, which is a lot. You can download it. Do not try to do it on the Wi-Fi, though, because it's going to take a lot of time. But this is the kind of data that we're going to be using to train our models, and that it's going to inform the machine learning models how we write code. One of the things that we need to do in order to do this is we want to minimize the amount of data we have. And one of the ways of doing this is finding all of the repositories that are copies of each other. And we do this by identifying different commits that are exactly the same. If you find 2 different trees that have the same root, then you know that those were actually originally the same, so you can unify this, and it minimizes the number of copies of the same blob you may have. We just published a blog post, so if you're interested in learning more about this big data set and how we created it and why we created it, you can find it on blog.source.tech. It was published yesterday. Oh, if someone wanted to take a picture, I saw someone. OK, the next step is, now that we have all of this data, what do we do with it? We need to analyze it. And what does it mean to analyze source code? Well, what is source code, right? This is a short Go program. It says, hello, Copenhagen. And you can interpret this as a sequence of bytes, right? So basically, P, A, C, K, etc. And this is a way of representing the thing, and it works. And you can train a neural network with this, just the bytes, and you can already do interesting things. We'll actually see an example of something that learns directly from byte by byte. The problem is that when you're doing this, you're actually hiding a lot of information that we already have from the program, right? We know that those spaces actually are meaningful, and the PACKAGE is actually a package, and that's a token, and we should consider it as a thing rather than a sequence of things. So you can also do byte tokens. And this is a different thing. And now we're still talking, rather than sequences of characters, we're still talking about sequences, but they're sequences of tokens. And rather than having a small set of possible values, we have actually a huge set of possible values. The number of letters, the number of characters in a given program is actually pretty small. The number of possible identifiers is actually infinite. So we have a lot of issues related to that, which is actually kind of the same issues that you will find in NLP when you're working with words. One more way to do this is abstract syntax trees. When you take a program and you parse it, which, by the way, the abstract syntax tree on the left doesn't match the code on the right. Do not try to match them. The abstract syntax tree is kind of going one level higher, and it's actually bringing more of that structure of the program to the model. The problem is that, of course, now we're not learning from sequences, we're learning from trees, and this is much, much harder. And last, but definitely not least, because this is where all the research is based on, is if you start creating extra links on that tree, what you get is a graph. So there's a bunch of different kinds of graphs we can learn from. There's cross-references of where this thing was defined. You have control flow graphs. We have all of different kinds of ways of interpreting what a program does. You can do this and learn from those graphs. And there's a lot of papers on how to do this in many different ways. So we can learn from sequences, from trees, and from graphs. And of course, sequences is the easiest. Trees is a little bit harder, and graphs is where it starts to get interesting. So what do we need also to create those graphs and trees? There's actually a lot of different things I need to do. In order to parse a program, you need to know first what programming language it is. So you need a tool that will tell you what programming language a file is reading. And this seems like an easy thing, because go.java, Java. What is .m? Well, MATLAB or Objective-C or something else, right? So actually, you need to also look inside. We wrote a prompt. We have Henry is a project that does this. Then you need to parse the program. And when you parse the program, you need to create an abstract syntax tree. And that abstract syntax tree, we want to make sure that is usable by any model, no matter the language. So we actually create this concept of universal abstract syntax tree. And a universal abstract syntax tree is simply an abstract syntax tree for which we agree in a format to store it. And also, it has language agnostic annotations. So it's saying, this is a function, this is a variable, this is a string. Those things are the same no matter what programming language you're writing, right? Whether it's Python or Haskell or Erlang, a string is a string. So that's the kind of language, the language agnostic universal annotations we do. Then we need to also do token extraction. If I say, hey, I want to extract all of the function names, I need to do that, right? I need to parse, again, the tree, go to all the tokens that match the description that I want to, of the things that I want to extract, and do so. Finally, history analysis, because most of the time, what you want to do is predict the future. And if you want to predict the future, you need to understand the past. Luckily for us, all of the past is actually encoded in the Git repository. You have all of the possible revisions of that project. So you can actually learn from that, and there's a lot of analysis on that part. And finally, reference resolution. In that code, when I say fump.println, println is a function defined in another package called fump, right? Actually figuring those things out is quite hard. Luckily for us, Google had done it before, and there's an open source project called Kite.io. And unfortunately, the documentation is not great. It's pretty hard to use. So what we did is we hired the creator of the project. That makes it easy. He just joined recently. We put all of this together, all of the different tools that we do for data analysis of source code in a tool called the engine, the source engine. And it is open source, Apache v2, it's free to use, so have fun with it. And I wanted to do a really quick demo of some of the concepts that I showed. So this Babblefish, the thing that is going to do the language agnostic parsing. So on the left side, on the right side, you have some Java, and on the left side, you have an abstract syntax tree. So say you want this is going to say that that is a node of type UAST string. That UAST string right there, let me highlight it more. That UAST string is a universal annotation. This is the same no matter the language. And the token extraction means that you can use XPath to extract those tokens. So you can do UAST string. Now you get the two strings in this program. The interesting thing, and why this is something that we use, is that if you use any other programming language, say Go, you also get something that kind of looks the same. On the right side is the same format, and you can use the same annotations to extract the tokens. So now you can see all of the strings also being highlighted there, right? So this is the project that we created to be able to learn from trees. We don't want to learn from the result of parsing a Go program and then having to redo the whole thing to learn from Java. So that's why we're learning from trees at a higher level. Then we put all of that inside of Git. So now you can do select star from repositories. And now you can run that and say those are the repositories. You can do from files, live coding, limit, let's go limit to, because I'm depending on the Wi-Fi, and then you can do things like, I want the language of the file path and the blob content. And when you do this, it's going to use one of the previous projects to actually tell you what programming language it is. You can also use UAST, the function UAST, to extract the tokens that you care from that program. So you could do things like, give me all of the functions that have been modified by this person during the last month, right? All of those things, the history plus the parsing plus the metadata, can also be merged into one single SQL query. And finally is all of this is MySQL. So if you know how to use MySQL with Python or any other thing, you can also do it. So here, I will not show everything, but there you go. So here with this query, we're extracting the language and then extracting all of the function names in that program, no matter what program it is. I don't care the programming language. We just parse it, extract the things, and count them. And then with a little bit of Python and what's the name? NumPy and PyPlot, we're able to generate things like word clouds and stuff like this, right? These word cloud, for instance, is the most common words that we found, the most common function names that we found for Python, which is __ init, for Go, for Java, for PHP. The interesting thing is that all of this analysis is done in a language agnostic way. And this, the most important point is all of the tooling that we want to do needs to be language agnostic because we want to be able to migrate to newer languages as they come without having to retrain all of the things we've done. Training over 3 terabytes of data is a lot of training. Okay, so challenge number 3. Now we have all of the source code, we have parsed it, we have abstracted syntax trees. How do we learn from this? We use neural networks, and I'm not gonna get into the detail of what a neural network is. How many of you have used a neural network, or implemented? Okay, so we all know what neural networks is, that's great, because otherwise I will not have the time to explain it. But for those that have never used it, I like to think about neural networks as simply a mathematical object that allows you to learn by example. You keep on saying, hey, if I give you this input, this is the output. And you keep repeating that over and over and over and over until it learns, and we call that training. So if you think about it, it's kind of like if you have a pet, and that pet you keep on training and training and training and training. At the end, the pet will do whatever you want, and the pet might be useful eventually, right? But at the beginning, they're pretty useless. Neural networks, not pets, they're cute. So typical example is MNIST, which is the hello world of machine learning, basically. And what we're doing is learning to predict what number is in an image. That image is, if I remember correctly, 28 by 28 pixels. And basically, you're passing all of those pixels as inputs to a neural network, and then you also have the label. It's basically, that is an 8. And then you train it and train it and train it. And the way you train it is basically, you try to predict, you get it wrong, and then you change it by doing gradient descent, which I will not get into the details, but by doing this over and over, the different weights in those neurons inside are going to change until you create something interesting. So, what can we do with this in code? Well, if we have tokens, you can say, I'm gonna get 10 tokens, right? And I'm gonna try to say, if I give you 10 tokens, predict the next one. That is a thing that you can do with machine learning, and it's actually something that I've done, and it works quite well. So for instance here, for I equals 0, I is less than 10, I what? Well, it's gonna predict plus plus. The interesting thing is that actually, if we go back here, you see that 0 is actually not 0. It's somewhere around 0, and that 1 is somewhere around 1. And this is something that we're gonna be using later. What if instead of working with 10 tokens, I actually want to work with all of the tokens, a sequence, and we don't know the length of that sequence? We can use recurrent neural networks. And a recurrent neural network, you can think about it as recursion. It's basically a neural network for which one of the inputs is one of the outputs from the previous step. So it's able to learn more interesting things about sequences. And this is the kind of neural network that you're going to use for problems like human language translation or sentiment analysis. Is this text positive or negative? Well, we don't really know how long is going to be the text, so this is the kind of network that you're gonna use. And we can also use it for us because, again, we have sequences everywhere, so those sequences work really well. One of the things you can do is, the traditional thing is learn how to speak like Shakespeare. And that works really well, because when you're generating Shakespeare, when you generate weird Shakespeare, it's still Shakespeare, because Shakespeare is weird, right? Like, if you create a weird name, it could be Shakespearean. You really don't know unless you've read the whole thing, right? So I tried to do the same thing with source code. I fed, rather than the whole works of Shakespeare, the whole works of the Go team, which is the standard library, right? The Go community, rather than the team, actually. And I was able to achieve 61% on the prediction. So basically, if you were telling me a given number of a sequence of characters, I was able to tell you which was the next one correctly 61% of the time, which is awful. It's actually really bad. And it is normal because we're learning from sequences, not trees or graphs, right? We're giving a pretty low quality data. So that's why we get pretty low quality predictions. So before training, you get something like this. If you ask the neural network, hey, generate some Go, it just does this, which is not Go. I think it might be Erlang. No, just kidding. Just kidding. Just not here. Okay. So now this is not Erlang either. But after one whole epoch, which is basically seeing the whole data set once, it's able to generate things like this. And there's a lot of things that are really interesting here. This is not Go. This will not compile. But there's a lot of things that look very familiar, right? And one of them is if error is not nil, return error. And that is what I call idiomatic. That's in Go, if error is not nil, return error is something that you see everywhere. So it does make sense that the neural network actually learned that quite fast. If you continue training, it keeps on getting a little bit better, but still this will not compile. Like if you look at this, that if ERS, that not ERS, that will probably not compile. I don't think it's ever seen code like that really, but you know, it looks like it could be Go if you look from far away. You keep on training, keeps on getting a little bit better, but not really that much. So what about graphs? Learning from graphs is also very hard. And actually, the best paper that I recommend is, Learning to Represent Programs with Graphs. That's the name of the paper, by Microsoft. And this is a great paper and introduces one problem that I really, really like. Because I think that this problem, called var misuse, could become the basic benchmark of machine learning on source code. If you think about computer vision, you have, I forgot the name, that data set with all of the pictures that we use all the time. Someone else knows it? It's the data set with all of the pictures. Sorry? Yeah, ImageNet, there you go. So ImageNet, the whole thing is, we have a huge data set with pictures and also labels on what you can see in those pictures, and the challenge is to actually match that. In here, what we can do is imagine that the data set is all of public Git archive, 3 terabytes of source code. And the problem is, I'm going to give you a program, and I'm going to remove one of the identifiers in the program. And you need to guess which one it was, right? The great thing about this problem is that it's already labeled. You don't need to predict anything. You just need to predict the thing that it was already there. You just remove it, right? So creating this is actually very straightforward. And this gets a decent amount of decent accuracy, but still not perfect. This is actually something that was used to find issues with IntelliSense on Microsoft codebase, on the .NET Core codebase, if I remember correctly, and they were able to find hundreds of bugs, right? So this is actually already really interesting. And we will see how we can use it later, even though this one is pretty obvious. Another one that I really, really like, it's called Code2Vec. And Code2Vec, what it does is learns from graphs, not trees anymore, but actually graphs, by actually finding the paths that are in between every single node in a tree. And then we learn from those paths. And we try to figure out which are the most relevant to our problem, to our prediction problem. And you can see like those those wider lines are supposed to be the most relevant paths. So you can see that these elements, return true, return I, those look very similar, but actually every single one of those functions is a completely different thing, and we would name them completely differently. So if you want to know more about all of the research, we have this data set. Well, it's a repository with all of the research that we've read at Sourced, and also some of the research we've written ourselves. It is a lot of things, so if you want to have fun, just go start reading. Some of them have a label saying they're good for beginners. I would definitely start with those because it gets really complicated really fast. Okay, so what can we build with this? And I had a demo, actually, that I wanted to show you. Okay. So I wrote this code, and it's already done because training takes pretty decent amount of time. But what I did was I got all of the code in GoGet, which is one of our packages, and I train a neural network with it. The way I trained it is not really important. I'm using Keras. This is the neural network that I use. It's a neural network with 50 entrances, 50 entry points, and then from those 50 entry points, no, sorry, not 50 entry points, is, I forgot the way it did it. Yeah, it's 50 entry points, it goes from 50 to 20, and then basically it reduces that into which one is the next token. And it does it only on specific length of characters. So this is not a recurrent neural network, this is a traditional neural network that works with n tokens. Just to make it simple. After training, you can see that the accuracy starts going up quite fast. It reaches 68, 68, 69, 69, 69, 70, 70, 70. It doesn't really go higher than that, even if you keep on training it. But even with this, actually we can do quite interesting things. So here, for instance, you can say, hey, I have these tokens on the left. So this, what it's doing is 5 tokens on the left, 5 tokens on the right. Guess the one in the middle. So this is doing I colon is equals 0, I something of 10, then I plus plus, and the brace. And you run this, and it tells you that there's a 91% of chances that it is less than, right? And this is great, but the interesting thing is that we don't want to use that number. We want to use the rest of the numbers. This is not predicting what is the chances for less than. This is predicting what is the chances for every single one of the possible characters that we have. Which means that if you actually find in the program more, greater than, you can compute the chances of having that. And it's less than 0.3%, right? So it's a very, very, very low chance. So we can actually say it's probably worth putting a warning there saying, did you mean less than, right? This is something that you can do already today. So what can we build? So as I was saying, you have those neural networks, and they're creating predictions. What we are trying to do is, rather than using those predictions to predict things, we're trying to use the rest of the predictions to find anomalies, right? So rather than being interested by the ones that are saying these are the highest possible ones, what we're trying to do is, you wrote this, how possible or how probable is it that this is the right thing? And once you get to a high level enough, a low level enough in this case, then we can say, this is suspicious, and we can mark it. So we use this, and we add it to GitHub. And this is an experiment. This is still not public. But what we did was, say you have pretty large code review. Imagine if instead of having to read every single line of code one after the other, you were able to say, hey, tell me what's interesting here. And it marks something like this. And that interesting is, it doesn't mean it's wrong. It just means that we were not able to predict that easily, which means that there's a lot of entropy. So it's interesting. So you should definitely review it first, or at least have a better look at that than the rest. Hopefully, you're a great reviewer, which means that you will review every single character, one after the other. But probably, you will not do that. So having something that is going to point you at, make sure you look at this before you continue, would be really, really useful. So the biggest difference is, as I was saying, the prediction versus expectation, right? Here, there's a mistake. Is there a mistake? Yes, there's a mistake, right? If you see this code in the wild, probably you would not pay attention to it. It looks pretty normal. But actually, oh, it does. There was an animation that went away. That is I minus minus should be I plus plus, right? If you were able to highlight that, going like, maybe this is a very interesting and exotic program that actually is supposed to do this, but are you sure, right? What about var misuse? When we use var misuse, we can detect a problem that happens very often because the software developers, we are lazy, which is great, which is we use copy-paste. And we use copy-paste. When we paste, we need to modify things. And sometimes we forget to modify some of them. So in here, what I'm doing is I'm copying from file A to file B. and I'm doing so in Go. And in Go, what you do, you open a file, and then you say defer closing it, which means at the end of this function, please close it. There's a mistake in here. The to file will never be closed, right? Because we copy-pasted, of course. And that's what you should be doing, really. But copy-pasting can be dangerous, and you can introduce issues like this. So var misuse can be a way to find these kind of mistakes in the source code and provide them at code review time. What about code to vec? Well, the code to vec thing is really interesting because it's going to allow us to understand whether the name of a function corresponds to what we expect. And more than that, it means that we're going to be able to understand functions not from a syntactic point of view, but from a semantic point of view. We're able to even generate things like, given a function, create a natural description. We did something which is an awful idea, so I will not even show you the source code, but it's something that writes the documentation of your programs by itself. It kind of works, and it generates things like full sentences that look like, you know, it could be written by a developer. If you really pay attention to what it's saying, most of the time, it really doesn't mean anything, which, depending on the developers, you know, that happens. But in here, you have contains and has for that one. On the right side is find an index, right? The interesting thing is, because of the way code to vec works, and the way we're doing embeddings over that, we're able to find two different pieces of code that are very similar, because they look very similar to each other, but actually give completely different predictions. And another thing that we used is we decided to create a deep learning identifier splitter. What we did here was, and there's a blog post on all the details of this, but we used the engine to generate a list of all of the identifiers of all of public gate archive. And then we store those. And then we use some well-known ways of splitting things. We say, it's Go, Java, you use camel case. So if you see that difference in casing, that means that those two things could be split, right? If it's for Python, even easier, underscores, right? And then what we do is we remove that information. So we make everything lowercase and remove all of the underscores and try to predict what was the previous casing. And by doing this, we're actually able to predict things like, did someone write my variable with a lowercase v, which is actually going against the guidelines of the way we write code. So I'm not going to show you the learning Go because that's already what I showed, but I will share the links so you can have a look at the way I did to generate that garbled version of Go and then how it starts getting better over time. Code to vec is something that we did not create, but this is an amazing demo. This is something that was created at the Technion University in Israel. And what it's able to say is, given this function with all of this code, what is the name of this function? What we do is we parse it, we get the tree, we identify which paths are the most relevant, and then we're able to deduct or predict that this should be called sort. And here, we're iterating over an array of elements. And once the element that we find corresponds to the one we were looking for, we return true. What is the name of this? It contains. Sure, but what if instead you return target or null, and you return object? Well, it's get target or get or lookup, right? So by changing the code, we're able to find different names. The interesting thing about this is that, as I was saying, it's not only about naming a function, because we all name functions, but it's actually finding how different combinations of functions could be named. So say that you have count. What is the closest things to count? And these are all of the different names that were embedded into a similar point in the space of the embedding. So count, get count, size, index, sum, max, stuff like that. All of these things are pretty related. So if you're searching for one, maybe you don't want to find only the functions called count, but also if something is called size, it's also something that you might want to return. Combinations. What is equals and to lower, right? Well, equals ignore case. Sure, if you do to lower and then you do equal, that is the equivalent. The interesting thing is you can do it also the other way around. So if I tell you, hey, I want you to find a function called equals ignore case, or you describe in natural language what equals ignore case corresponds to, you will be able to say, hey, we don't have that function, but we have these two functions that when you put them together, that's the same. So maybe you want to use those. And then this is my favorite, this analogies. Embeddings in NLP, the traditional example for embeddings is if you get the vector from man to woman and you add it to king, you get queen, right? So man is to woman as king is to queen. Well, receive is to download, as send is to upload, right? You can do the same thing here. Find which are the opposites or which are kind of the same, but in the past. All of these things, like those, all of that information is actually encoded in the embedding. And finally, the neural splitter. And I'm actually using this called Colab. A Colab is amazing. I do not work at Google anymore, so I don't need to sell it. But this is amazing. You get TPUs for free, so use it. So here, I'm going to download our already pre-trained model. Okay. Then we're gonna load the model. And then we're gonna be able to do things like this. So if you try to split, I think this is a variable, it's actually going to say, I know which words are in here, and it's going to split it. If you say, I'm in Copenhagen. I think it's written like that, right? I mean, oh, no. Okay, that example is very hard. I'm in Denmark. Denmark? Nope. Oh, wow. This is bad. Yay. Then you can use the same things, the same concepts that once you have separated, you can actually put them back with camel case or whatever. So you could say, for instance, if someone wrote, I think my time is over, but they forgot the capital O on the over, you can actually predict that and say, actually, that's not how you write it. So what are we doing with this? We are trying to empower developers to review code better. Why are we doing code review? Because giving feedback to developers before they're ready for it is actually quite dangerous. If you have something that creates warnings on your editor, and it keeps on getting that wrong, it's going to be really annoying. And even if it gets it right, but it takes more than a second, it's also very annoying. So what we're doing is, rather than trying to make everything incredibly fast and accurate, is we're moving it to the point where humans are going to be reviewing it. At this point, developers are ready for the feedback, and they can get all of the information. More than that, when I was working at Google, I was working in the Go team, which meant that when I was writing Go code, I got code reviews from people like Rob Pike, which is really cool, also kind of scary. But the good thing about it is I was able to learn a lot. It was by far the best experience I had at Google, was learning from other people. And the problem is that you cannot make that scale to everyone in the world, because actually reviewing code is pretty time-consuming. So what we're trying to do is to reduce that, to enable reviewers to do their job faster and better, so more people will be able to enjoy those code reviews. So putting everything together is Lookout, which is our project that already works, and I will not show it because I want to leave some time. Actually, I will show it really quick to show you how it works, because I have some time. So if you go to pull request, they were all closed? No, okay. You will see that the way this works is someone creates a pull request, and as soon as this is created, the bot is already replying with a bunch of different pieces of feedback. Here, for instance, it's saying, hey, this function here, it actually looks a lot like this other function, util grpc helper logger. This is in the same file. So this is something that probably a code reviewer would notice and say, you've created two functions that look a lot alike. It's probably worth merging them together. This is actually machine learning, by the way, because it's not just actual clones. It's close enough that we consider that it's worth merging them together. But also this does it over all of the repository and the dependencies. So if you end up writing some code that actually looks a lot like a function that it's already written somewhere else, we'll be able to detect that. And that is something that human reviewers cannot do. Or they can do if they know all of the code base completely, which, it's pretty rare for any code base. So what else are we doing? Well, the first thing we're doing is actually automated style guide enforcing. So figuring out whether the new code that you send corresponds to the style, to the formatting of the code that is already there. So rather than having to enforce rules, specific rules are formatting, we can instead enforce coherence and just make sure that the new code looks like the previous one, right? That is mostly what you want to do. So we can do that automatically. Also bug prediction. Eventually we'd like to do automated code review. Make sure that we can just say, the pod says yes, you can merge. Who knows, maybe one day. Not today, for sure. Code generation, if once we have all of these embeddings, we're actually able to even select tests from a given test suite. So say, hey, I want to write a test about these things. Find which piece of code corresponds to the thing I want to test. And also natural analysis, natural language analysis. There's a blog post written by GitHub recently where they find pieces of code according to the natural language description. It works with the same thing, with Code2Vec. And finally, education. I really care about empowering new generations of developers to learn as much as possible. And the problem is that code reviews are not the most efficient way to do it, but they're still the best. So we want to make sure that that way of teaching, which is so great, becomes even more efficient over time. So will that mean that in a couple of years, you will not have a job? No, because if you think about it, when CAD was created, do you think that architects really considered that they will lose their jobs? No, it actually empowered them to create better things. And that's what we're trying to do with ML and code. If you want to know more, source.tech, and also we're hiring, and also we are hiding somewhere in a table behind all of the coffee. So if you want to find us, we have a booth. It's just very hidden. You can also find awesome ML and code. That is all of the research that we've used. And also, I have stickers and an email. So if you have any extra questions, you can send them there. Thank you.